All right. Well, here is the test number 5 right before Thanksgiving. Let's blow through this thing. Question 1: Is the graph a linear function? Why or why not? Well, what we need to always remember with linear functions is that the key idea to keep in mind is that a function is linear if the rate of change, the change in y over the change in x, if that is constant. Another way to think about it is that all graphs that are lines have constant rates of change. So what we can do is we can see that if we draw a line here, we know that no matter where we measure the rise and the run, which is our rate of change, which is also our slope, no matter where we measure that, it's the same at any point on the line. Those are all the same. So it's a constant rate of change. So let's take a look at our graph over here. We see that it's a parabola. This is a quadratic function. And the rate of change, well, like the rate of change here is different than the rate of change here. I'm just drawing tangent lines here to show you the different rates of change. The rates of change are different at all points on this graph. In other words, this graph is not a line. Therefore, it's not a linear function. So why or why not? Because of the rates of change. This graph is not a function because I'll just abbreviate ROC, rate of change, is not constant. Okay. Number 2, is the table a linear function? Why or why not? Well, we could always plot these points. We could easily just draw our little axis here and go 0, 4, 1, 7, 2, 10. Oops. I did that first one wrong. 0, 4. We could go 1, 7, 2, 10, 3, 13, and it would make a line, but I want to prove it to you analytically also. But just know that that's a backup that you can keep in your back pocket if you don't remember the following. We'll measure the change in y, and we'll also measure the change in x, and then we will come over and see if the change in y, remember, that's like our rise, divided by our change in x, which we can think of as the run, is constant. So let's take a look here. From 4 to 7, that's a change of positive 3. From 7 to 10, that's a change of positive 3. From 10 to 13, change of positive 3. Let's look at x now. From 0 to 1, that's a change of positive 1. 1 to 2, change of positive 1. 2 to 3, change of positive 1. Well, the answer will soon become clear. Change in y over change in x for this point here is 3 over 1. The rate of change here is 10, I'm sorry, no it's not. It's also 3 over 1. And the rate of change here is 3 over 1. And they all equal 3. So, is this a linear function? Yes. Why? Because the rate of change, remember, which is the same as delta x over delta y over delta x, is constant. So, rate of change is constant. And I'll just use those abbreviations there. Okay, and so just keep in mind that this idea, this change in y divided by our change in x, is the exact same idea as what we did up here, measuring our rise, which was our change in our y-axis, divided by our run, which is our change in our x-axis. That's why the slope is the rise over the run, which is the same as delta y, change in y, over change in x. All these ideas run together. All right, let's take a look. Let's scroll down some here. Number 3, which of the following situations can best be described by a linear function? Well, let's read that first one. The height of a soccer ball after it's kicked as a function of time. Well, here's our time. Here's the height of a soccer ball. Well, if as the soccer ball is kicked off the ground, the height is increasing, and then it reaches a peak, and then it comes back down. This is not a linear function because, well, initially the change in the height is positive, and then over here we see that the change in the height is negative. So for one thing, the height is positively increasing, the rate is positive, and then on this side as the soccer ball is coming down, it's negative. So we can immediately say that the height of a soccer ball after it's kicked is not a linear function. I'll just write no right there. Let's take our thinking one step further. What would it look like, let's say we were playing soccer on a planet where there was no gravity? Well, you kick the ball, and it just keeps going up and up and up and up and up and up, and then the ball never comes back down because there's no gravity to bring it down. Well, now is the height increasing at a constant rate? Well, yeah, the way I've drawn it, it's a linear function. So yes, so in that case, if there was no gravity on your planet, then height would be a constant rate. So the key to ask yourself when you're reading these is figure out what is the rate, and is it constant? So number 2, the distance traveled at 50 miles per hour as a function of time. Well, right here, the rate is given to us, miles per hour, and it stays at 50. And lastly, the volume of a sphere as a function of the radius. Well, the way I like to think about this is that, say you have a deflated balloon, and you initially blow one breath into it. The size of that balloon increases pretty dramatically, right? You notice that balloon immediately start taking shape. Well, let's say 20 breaths later, your balloon is huge, and let's say on that 21st breath, are you going to notice the same amount of change in size as you noticed in those first breaths? No, you're not. So the radius, the volume of the sphere increases, it increases in a cubic fashion in relation to the radius. So no, that can't be represented by a linear function. Let's take a look at number 4. Are those graphs linear? Well, it states that they all are linear because they all have a constant rate of change here, but are they all functions? Well, the quick and dirty way to tell if they're function is to draw that vertical line test, and we see that when we draw that vertical line, both on B and C, it intersects at only one point. But let's take a look over at A, and when we draw a vertical line through A, it intersects at infinite points. So no, that's not a function. Why is it not a function? Well, when we look at that one x, it looks like this vertical line is drawn at x equals negative 35. How many y's are there?